Good morning, good afternoon, and good evening. This is our final webinar of the year, and we want to thank you all for joining us and let you know that we greatly appreciate your taking time out of your busy day to join us. I'm Tom Concolino, and I'm here with our presenter, Aya Takase.
Hi, everyone.
Thank you again for attending Rigaku's webinar series on X-ray Computed Tomography for Materials and Life Science. This is our 8th segment, Metrology Applications. It will focus on the principles and techniques researchers use in evaluating materials for industrial applications. We will review industrial metrology and discuss when CT works better than traditional methods, such as CMM, a coordinate measuring machine, which Aya will review. We'll also discuss how to process CT images to obtain accurate dimensional analysis results. Aya will also offer methods for dealing with the unique challenges of performing CT experiments on material science samples. Now, please note, if you missed any of the previous webinars, you can view them on the Rigaku website. And before we start, a few housekeeping items. As far as today goes, as usual, we'll be taking questions during the live webcast. We ask that you submit those questions via the Q&A button at the bottom of your screen. We will not be monitoring the raised hand or chat features. We will be saving the questions you submitted during the webcast, and we'll answer as many as we can during the Q&A session at the end of the presentation. If for whatever reason you have difficulty viewing the live webinar, please note that it is being recorded and you'll be able to view the recording beginning tomorrow. Also, at the end of today's presentation, you'll be directed to a survey asking for your input on what topics you'd like to see us cover in 2021, and your feedback is greatly appreciated. Okay, and with that said, I would like to introduce our speaker for today, Aya Takase. Welcome, Aya.
Thanks, Tom, and thank you everyone for joining us for the webinar series, X-ray Computed Tomography for Materials and Life Science. Today, we will talk about metrology applications. When you build something, it's important that everything fits and the movable parts move smoothly. And when there are many parts, you might want to check if those parts' shapes and sizes are correct before investing a lot of time in assembling them. Or you might want to know if there is something wrong about those parts before using the assembled product, because otherwise things can go wrong. For those and many other reasons, measuring individual or assembled parts, namely metrology, is an important part of the designing, manufacturing, and quality control processes. So today, we're going to discuss how we can use X-ray CT for metrology. So in this webinar, you will learn some keys to metrology using X-ray CT and analysis techniques, and we'll take a look at a number of metrology application examples. So what is metrology? Metrology is the science of a measurement, which is probably a little too big of a subject to cover in one webinar. So today, we're going to focus on industrial metrology. Industrial metrology is the application of measurement to manufacturing and other processes. And roughly speaking, there are two types of measurements. One is just a normal measurement, and the other one is geometrical dimensioning and tolerancing, or GD&T. In a nutshell, GD&T is a little bit more involved measurements, and you set the tolerances with the function of each part in mind. And I'm going to explain the difference between the two just briefly and introduce some GD&T terms, which we will be using in this webinar later. So let's say that we have this cube and we want to know how big this cube is. For a normal measurement, you can just take a ruler or a caliper and just measure how big this cube is. And you would do this in an arbitrary coordinate system. But for GD&T analysis, you would place this cube in the XYZ coordinate system. And this is one of the major differences between the two. Or you might want to know how big the cylinder is. And again, for a normal measurement, you can just pick one point and measure how big this diameter is. But for GD&T analysis, you would be measuring multiple points on this surface so that you know the best fit diameter or radius and its variance. You will note the maximum and the minimum of those values too. And you do this in XYZ coordinate system, so you will know the location of the cylinder and the variation of the location as well. So again, when you're looking at a cylinder and you're doing just normal measurement, you can just check the diameter and the length, or you can apply GD&T analysis to check the location, the orientation, and some of the form factors of the cylinder. And you might have seen those before in some drawings, but people use GD&T symbols to describe each measurement and a tolerance. For example, this symbol represents cylindricity. This parameter is about how close the cylinder is to a true cylinder. If you're looking at a flat plane, you might want to know the flatness. For the orientations, you might want to check the perpendicularity or parallelism. And for the location, you can check concentricity or position. And those are just some examples. And depending on how you count them, there are more than 14 GD&T symbols describing different types of measurements and tolerances. So you can see that the normal measurement and GD&T analysis are a little bit different. But the important point I should have mentioned here is that you can do them both using X-ray CT. Now, when you think about this type of dimensional analysis, you might think of a CMM, or coordinate measuring machine. So how is CT different from CMM or other techniques you can use for dimensional analysis? So let's take a look at them. So you can use a coordinate measuring machine, or CMM, to do dimensional analysis. You can also use an optical scanner, and you can use an X-ray CT scanner as well. And those three techniques, and often used for dimensional analysis, use very different physical phenomena to do the measurements. So CMMs use a tactile measurement. So you would take a physical probe and let it touch the surface of the object to measure where that surface is. So this is a tactile and a mechanical measurement. The optical scanners use optical reflection on the surface of the object. And the X-ray CT scanners use X-ray absorption contrast for the measurement. And because of the difference between those three techniques, physical differences, there are pros and cons for each technique. So let's take a look at the CMM first. The CMM is probably the most well-established technique, and that's a pro. And also, because this is a tactile and a mechanical measurement, it is the most accurate technique. And you can deal with relatively large objects. So those are the pros of CMMs. But there are some limitations too. Because this is a tactile measurement, you would have to select several points to measure. You really cannot scan the entire surface. Or if there is a small space you can't really put the probe into, then you cannot do measurements. And it's the same thing for enclosed internal structures. So that's for the CMM. The optical scanners can scan the entire surface. You don't need to select several points. So that's a pro. And this technique can also deal with relatively large objects. But if the object is transparent, that would make the measurement difficult, or something is enclosed inside of something else, or internal structures, you really cannot see using optical scanners. Now, let's talk about the CT, today's topic. The biggest advantage of the X-ray CT technique is that you can scan the entire volume. Not just the surface, not just selected points, you can scan the entire volume. And this means that you can measure internal structures, including voids and cracks. But this technique comes with some limitations, like anything else. And the biggest limitation of X-ray CT technique is the sample size. Because we are using an X-ray absorption contrast technique, if X-rays cannot get through the object, you really can't image it or measure it well. So the sample size is somewhat limited. And the other thing to keep in mind is that when you have a mixture of very light material and a very heavy material, for example, if you have a metal piece inside of a foam, then that can cause a lot of beam hardening artifacts, which we discussed in the first episode. And those artifacts can skew the measurements. So that can be a little bit challenging. Now, I said that the good thing about the X-ray CT technique is that you can scan the entire volume. But if we're scanning the entire volume, how do we define the surface? That's what we measure. The surface is the measurement point. So let's think about this question next. So this is aluminum, machined aluminum. It's about 2 inches in diameter, and it has a bunch of cylinder-shaped holes inside. If you do a CT scan, you're going to get some sort of gray level image. And this is essentially a digital twin of the original object. So we can use this image to do the measurements. But to do so, we need to define where the surface is. So let's take a look at a cross-section of this image. And we're going to zoom in. Now, the black areas are air, and white or light gray areas are aluminum. So the borderline between those two areas, for example, here, is the surface. And we're doing the volume scan. You will see the internal surface as well. To do the measurements, we have to digitally define where the surface is. And to do so, at least as a concept, we do the same thing as a CMM does. So we take a digital or virtual probe and put this probe into this image and figure out where black turns white. So that's the surface. And we do this probing work for the entire volume to define the surface like this. So once you define the surface, you can start taking measurements. Let's take a look at this cylinder-shaped hole. So we can look at this hole from the side and measure the radius, for example, but we are defining the entire surface, not just one point. So you can also get the minimum and the maximum and the deviation of this radius. So this is a distance measurement. You can also look at angles between two planes, for example, this one, and check how close that is to 90 degrees. So this one is a little bit short of 90. So as you can see here, once you do a CT scan and define the surface, you can pretty much measure whatever you want. Now, to get those scans, the gray level images, are there any special considerations? And there are a couple, and I want to focus on 2 major ones. First, you want to use high energy X-rays for large and dense samples. The samples or objects you deal with for metrology analysis tend to be denser or larger compared to more of a material science or life science based samples like the composites and foams. And the denser the material is, and also the larger the material, the sample is, the higher energy X-rays you need, because the energy of the X-rays needs to be high enough to get through the object to do a good imaging. Otherwise, you would get, again, beam hardening artifacts, which can skew the measurements. The other point is, you might be wondering why I'm showing this tilted building in the picture. Well, this is the reason. You want to tilt the sample. I will explain what I mean by this. When you have a box-shaped sample like this one, you might be tempted to just put it straight down on the table, shoot X-rays, and image it. But if you do it this way, X-rays need to go through this much of a distance in the sample. But if you tilt the sample a little bit like this and do exactly the same scan, the X-rays need to travel only this much. And the longer the distance X-ray beam needs to go through, the more beam hardening the artifacts you're going to get in the final image. So it's important to do this to shorten the distance. I'm going to show you an example. So this is a roughly cube-shaped plastic piece, and you can put this on the stage just straight down like this, or you can tilt it a little bit. If you keep it straight and do a CT scan, the cross-section is going to look like this. If you tilt the sample, the same one, and do a scan, it could look like this. So when you keep the sample straight, you're going to see those streaks coming out of the edges of the object. You also see the surface is blurred. You really can't see a good interface. You also see some streaks inside of the plastic. And those are all beam hardening artifacts. But just simply tilting the sample for 30 or 40 degrees, you can get rid of all those artifacts. So when you do X-ray CT metrology analysis, make sure that the energy of the X-rays you're using is high enough to get through the object you're scanning. And also look at the sample, the object, and think about its shape and tilt it to minimize the beam hardening artifacts. Now, once you do a scan and define the surface and you start taking measurements, then you might wonder, how precise is this technique anyway? So that's a good question. But the term precise or precision is a little bit of a vague one. So instead, I would like to talk about the resolution and accuracy of this technique. The resolution of this technique is about 1/10 of the voxel size. And the accuracy is when you do the correct calibrations, about 10 microns or less. And the second term here is coming from the measured length. This term is just telling you that the longer the measured length is, the greater the error can be. Now, let's think about where those numbers are coming from. First, the resolution. Everything we have discussed so far in this webinar series was based on pixel or voxel-based segmentation. And when you do the analysis that way, your resolution is limited to the voxel size or double of it. Then how can we get resolution better than the voxel size? The answer to this question is related to how exactly we define the surface. So let's think about this object. The cross section here looks like this, and let's zoom into this corner. So let's say that this is the actual cross section of the object. To image this using X-ray CT, we're going to use a voxel or voxel grid. And when you do that, you're going to get an image that looks like this. So the black part is air, and let's just call it 0% absorption. And the white part is the object, and let's call that 100% absorption. Then we have all those gray voxels in between. And we get those gray voxels because of the partial volume effect artifact, which we discussed in episode 6. And the gray level of those voxels can vary anywhere from 0 to 100. So how do we define the surface or the interface between black and white in this image? The simplest way to do it is just to threshold it at 50%. If you do that, this is going to be the surface and this is the object. Now, this doesn't quite look like the actual one. So we have to figure out a better way to do this. So instead of simply thresholding the image at 50%, we're going to take a probe and go from point A to point B. You cross the interface, then plot the gray value like this from point A to point B. Then calculate the average air level and average object level and figure out where the 50% line is. Then figure out where that point is on the line A to B. And mark that as the surface or the interface between black and white. And this point is here in the image. So you can see that when you do it this way, you are not bound by the voxel grid anymore. You can put the interface right in the middle of the voxel. And this is called ISO 50 surface determination. And you can calculate the average air or average object gray levels globally, but in many cases, the gray level can vary from part to part in the sample or slice to slice. So it works a lot better when you do this averaging locally. So we're just looking at a one probing, but you do this on the multiple spots on the interface. to figure out the entire surface like this. So this is how you define the surface more accurately to do metrology analysis. And what we're looking at here is just a cartoon version of it, but let's take a look at a real example. So this is a part of a piece of plastic, and you see the yellow line, that's the defined surface. Let's zoom into one area. So those thin yellow lines are the probes to figure out the interface. And this orange line is the defined surface. And you notice that this line is running right inside of the voxels. And this is how you can achieve 1/10 of a voxel size resolution. Let's take a look at an example we saw before. So this is the CT scan of the aluminum piece. And this scan was done at 69.5 micron voxel. And by doing the ISO 50 surface determination, you can define the surface at 7 micron resolution. Okay. If you're thinking that this looks like quite a bit of a calculation, like it kind of is. So what software can do this? I'm using BG Studio Max from Volume Graphics. This is a very powerful tool you can use to define the surface and also take all kinds of different measurements. And you can use this package to do GD&T analysis as well. Okay, so that's for the resolution. Now let's think about the accuracy next. How do we define the accuracy? This is an important question to ask ourselves if we're going to use this technique for process control or product design process. And there are several national and international standards available about X-ray CT accuracy evaluation. So there are several ASTM standards. And this one, VDI 2630, this is a German standard, but it describes how you can evaluate your system for X-ray CT accuracy very much in detail. And there is one from ASME. And there is one on ISO standard, but this one is still under development. So depending on the requirements you have for your project, you can select the correct standard and appropriate standard for your project, and then just follow them to evaluate how accurate the system you're using for X-ray CT measurements, and also the software you're using to define the surface and take measurements. In this webinar, I'm going to just talk about kind of concept of how we can evaluate the accuracy of this technique. So what you do is to take a calibrated standard, a sphere with a known diameter, for example, and measure that diameter using your X-ray CT scanner and software, and compare the two. And when you do this, most likely you're going to see systematic shifts between the two. And it's very important that you correct those systematic shifts. And for the standards, you can use precision ceramic spheres. Ceramic spheres work better than metal spheres because metal spheres tend to have a lot of beam hardening artifacts. Now, if you use a sphere, that gives you only one distance to measure, just the diameter or the radius. If you want to do this for multiple distances, you can use those ruby spheres used as probes for a CMM and place them at different distances and measure the distances of those ruby spheres using a well-calibrated CMM, and use those numbers as your standard to compare when you do a CT scan. Now, let's take a look at an example. So this is an aluminum sphere, the L203 sphere from Goodfellow. And this little sphere comes with a certified diameter of 20 plus minus 0.00125 millimeter. You can put this on a CT scanner, and we use the Rigaku CT Lab HX in this case. And you do a scan, define the surface, then you measure the radius in this case. The best fitted radius in this case came out as 10.0027 millimeter, and that is pretty close to the certified radius. And as you can see in this example, Once you do a CT scan and define the surface, then you can just click one or two buttons in the software to get 1100 points measured so that you can calculate the best fitted radius and also the variation of the radius. Anyway, you do this type of measurement by using different magnification factors or field of view sizes. You probably should even place the sphere at different locations inside of one field of view to do multiple measurements with different conditions to figure out the maximum possible error you get from your system. And this is a result. So if you don't do any calibration or correction whatsoever, the maximum possible error for 20 millimeter diameter measurement can be over 70 microns. But just by simply correcting or calibrating the magnification factors, you can bring this down to about 13 microns. And you might want to consider some artifacts. You might have to optimize the scanning conditions and do the process again. Then you can bring this maximum possible error down to less than 10 microns. And this is a relatively simple calibration. You can do more on involved calibrations to bring this error even further down. And I think the best number I've seen so far from X-ray CT is about 4 or 5 microns accuracy. Okay. So we just talked about the resolution and accuracy of this technique. Now, let me just summarize what we just talked about before we move on. The CT metrology can see the entire volume. This is the biggest advantage of this technique. And by doing an entire volume scan, you can see the internal structures, including voids and cracks. And by doing appropriate calibration, you can achieve 10 microns or less or better accuracy. And when you do use CT for metrology, make sure to run the calibration and always be aware of artifacts and optimize scanning conditions as necessary. Okay. So when is this technique useful? There are many areas you can use X-ray CT in, and one of them is just simple dimensional measurements. You can always use X-ray CT for this, but especially when you want to see internal dimensions, air gaps, or voids and cracks, the X-ray CT can be an excellent technique for this type of measurements. You can also use X-ray CT for GD&T analysis, nominal versus an actual comparison. This is a comparison between the CAD drawing and the actual object. You can use this technique for reverse engineering or even for mechanical simulations. So I'm going to show you a few examples for each category. So can we measure internal dimensions? Let's take a look at an example. So this is a Matryoshka doll or Russian nesting doll. And from the outside, you see only one doll. But if you use X-rays, you can see 1, 2, 3, 4, 5 dolls. So there are 4 more dolls inside of this big one. And this is just a 2D projection, but you can do a full CT scan and make outer dolls transparent to see what's inside, or you can cut and slice the CT image to do all different kinds of measurements. And what we're seeing here is just a 3D rendering image, but we can define the surface, and let's take a look at one cross section. This green line is the defined surface. And you can take whatever measurements you want using this CT scan and define the surface. So let's take a look at the height. The biggest one is 81.626 millimeters high. And this anyone can measure. But again, using X-rays, you can see this one and all the way down to the little one inside. And you can measure the height of all those dolls. Or you might want to know the waistline of doll number 3, then you can do that too. Okay, let's take a look at another example. So this is a CT scan of a golf ball. And a golf ball usually consists of an elastic core and a hard shell. If you want to look at the elastic core, you can digitally remove the hard shell and just look at it. And in this example, you can see the seam between two half spheres. Or you might be interested in the hard shell and do maybe thickness measurement. And if you do that, you get a result like this one. So in this image, the hard shell or the wall thickness is color coded. Blue is thin and orange is thick. And then when you look at this image, you might realize that this looks asymmetric. On the left side, the color variation is from blue to green. Those dimples are blue, 1.6 millimeters, and the thicker parts are probably 1.8 millimeters or so. But on the right side, it's more from green to orange. So they are overall a little bit thicker. And what this means is that the elastic core of this golf ball is not sitting at the center of the ball, which is probably not a good thing for a golf ball. But if you think that this one is bad, you should see the next one. So this golf ball is a relatively expensive one, about $50 a dozen. If you do the same analysis on a $12 dozen golf ball, it looks like this. So you see a whole lot more color difference between left and right. And in this case, the elastic core is probably about hundreds of microns shifted from the center of the ball. So this is one of the analysis you can do with X-ray CT. Now, can we measure air or air gaps in voids? And that's another thing you can do with X-ray CT. So let's take a look at this example. So this is a CT scan of a plastic bottle cap on the bottle. And the cap and the bottle have some air gap in between. And you can evaluate the air gap and color code it for the thickness of the air. So this is a cross section of the cap, and we're looking at this from the top. And this part, for example, has 2 millimeter thick air gap, and this part has more about 1 millimeter. You can look at a cross section here from the side like this too. And in this cross section, you can clearly see that there is a good contact between the cap and the bottle here. And there is about 1 millimeter gap here. And those are just two-dimensional cross sections, but you can visualize this air gap analysis in 3D like this to make sure that the air gap distribution is as designed. And you can also check if there's a good contact between the cap and the bottle all around so that the content of the bottle doesn't leak. And if you see anything that's different from how you designed it, you can investigate it quantitatively. So this is the air gap analysis. Let's take a look at an aluminum die cast next. Aluminum die cast is known to have a lot of air bubbles or voids inside, and you can see those voids using X-rays. So those tiny little speckles you see there, they're small. So let's zoom into one area here. In a cross section, you see those voids as black speckles, and those red and blue ones are color coded for their sizes. And this is just a 2D cross section, but of course we have fully 3-dimensional data for those voids. So you can measure their height or width, location, volume, whatever you want to analyze about them, you can analyze them and make a full list of all voids. And once you have this list, you can calculate things like the total volume of the voids or average size or maximum size of the voids. You can also look for hot spots where you have high density voids. Those are the areas that can be weak. So this is the void analysis. Now, can we do GD&T analysis? Yes. So let's go back to this aluminum piece and let's try GD&T analysis on this piece. So again, the first thing to do is to do a CT scan and define the surface. Once you define the surface, you can do a normal measurement, measuring the diameter, for example. But when you do this, you don't know where the XYZ coordinates are. to do GD&T analysis, we have to define the XYZ coordinates by using datum features. So for example, we can use this bottom plane as the primary plane, which can define 3 points in space, and pick another one as a secondary line, which can define 2 points in space, and pick a tertiary point, which will define 1 point in space. You have to use 6 points at least in space to define the XYZ coordinates. And this is called the 3-2-1 rule. And you can't really pick whatever features you want when you do this, because when you look at the GD&T symbols in the drawing, they're usually showing up with specific datum features you're supposed to use to measure that number. So look at your drawing and see what datum features you're supposed to use, and use those to define the XYZ coordinates. And once you define the coordinates, you can start doing GD&T analysis. So let's take a look at the cylinder again. So you can always measure the radius, but in this case, you have the XY coordinates for the cylinder-shaped hole as well. You might care about the cylindericity of this hole, then you can check that too. So we're going to look at those 2 cylinder-shaped holes. And let's say that the tolerance for cylindericity is 0.07 in this case. And the one on the right is within tolerance. The one on the left turns out to be out of tolerance. So that's cylindericity analysis. You might care about the flatness of the top plane, and you can check that too. And in this case, the tolerance is 0.1, and this plane is within tolerance. You can look at 2 planes to check the parallelism as well, and this one is within tolerance. So those are relatively simple GD&T analysis, but the idea is once you define the surface and define the XYZ coordinates using the datum features, you can start doing GD&T analysis. Now, can we compare a CAD drawing and a CT scan? This is the nominal versus actual comparison. So this is another thing you can do. Let's take a look at an example. So this is a 3D printed plastic part, and you see the CT scan on the right. This piece from the outside looks like just the white cube, but there are a lot of intricate structures inside, which might be difficult to measure from the outside. But once you do a CT scan, you have the full volume information, so you can use that as the actual measurements of this cube and compare them to the original CAD drawing you used to print this object. And this is the result of comparison. So green indicates that the printed part and original drawing match. Blue indicates that the printed part is smaller, and red and pink indicate that the printed part is larger than designed. And this is a great way to visualize where the discrepancies are. But of course, you can click on different spots to see the deviation between the two quantitatively. Now, we're still just looking at the outer surface, but you can look at the internal structures. You can even look at a cross-section here, like this. And if you want to know how well the printed part and the drawing match for the center hole in the middle of the cube, you can look into that too. And you see both positive and negative shifts in this case. Okay, so this is a CAD drawing versus a CT scan comparison. But can we compare 2 objects, 2 CT scans? And you can do this in pretty much the same manner. So let's go back to this bottle cap example. So those are 2 CT scans of the same plastic bottle cap. One was scanned with an open state, and the other one was scanned with the cap closed on top of the bottle. You can compare those 2 CT scans to see what kind of deformation this cap goes through when you close it. And this is the result. So again, green indicates that the open and the closed states look the same, and blue and purple indicate that the closed state has lower value, and red and pink indicate that the closed state has greater value. So this color variation is telling us that the cap gets pressed down on the sides like this, and the center part comes up a little bit. So this is the deformation this cap goes through when you close it on the bottle. Okay. Now, can we use this for quality control? Of course we can, and it's probably obvious that you can take some specific measurements in the width or height of a part and see if they pass the test or within the spec. But the example I want to show you here is a little bit different. So let's say that we make those plastic boxes, and this one is the golden standard. This one is right at the specs, whatever measurements you take. But we're not sure if those boxes are good or bad. Instead of just measuring the width and height of those boxes to test them, you can say something like the maximum deviation for 90% of the entire surface needs to be within 0.1, and compare the entire surface. If you do it that way, this box fails the test. Again, green means that this test object matches the golden standard, but blue and pink are indicating discrepancies. So this one has too much difference. This one is mostly green, so it passes the test. This one fails. So this is just a little bit of a different way to do quality control. Instead of selecting specific measurements, you can use the entire surface to see if each part passes or fails the test. Now, can we do reverse engineering? The term reverse engineering can mean many different things, but I'm going to just show you two relatively simple examples using the same plastic box. Now, let's say that we have this plastic box and we have to make another one, but we do not have the original drawings anymore. In that scenario, you can scan this object and convert the CT scan into a polygon mesh. And at this point, it's just a polygon mesh. So you can feed this into a 3D printer to make another one. So this is the use of X-ray CT for reproduction. But let's say that we need to make some modifications to this existing part. Then a polygon mesh is probably not the most convenient way to do the conversion. In that case, you can convert the CT scan into a CAD drawing. This actually is not a really trivial thing to do, but VG Studio just added this function, an ability to convert a CT scan into a CAD drawing. So you can use that tool to do this. Then now we have a CAD drawing file. So you put that in the CAD software, make necessary modifications, then print it or produce it. So those are two kind of simple ways to use X-ray CT for reverse engineering. Now, the last example I want to show you is an example of a mechanical simulation. A mechanical simulation is really not CT analysis, at this point anymore. But I wanted to show you this example to make a point that there are many different next steps you can take after you do a CT scan, and a mechanical simulation is one of them. So this is a CT scan of a water flosser tip. This is a piece of plastic and the entire volume has been scanned. And in this CT image, you can specify certain areas and say that this blue part is fixed and the red part is going to be loaded with a force of 50 newtons. Then simulate the von Mises stress distribution like this. So blue means that the part is not stressed, and red and pink mean that the part is very much stressed. And when you look at this result, it's mostly blue except this thin neck part. You see a lot of red and pink there. And this means that if you do this experiment of loading the tip with the 50 Newton of force, that's where this part is going to break. This is a simple example, so you can probably look at the part and say that, okay, that's where it's going to break. But if you have a component or part that has a lot more complicated shape, and you might have even voids and cracks inside, then it is not that easy to predict where it's going to break. But by doing a CT scan and applying mechanical simulations, you can predict where the part could most likely break. Okay. So we looked at a number of application examples, and I hope that you saw something that's similar to what you do or something interesting to you. And in closing, I just want to show you a short list of the next steps you can take, just to give you an idea. So once you do a CT scan, you can take those results as, let's say, volume mesh, and move on to programs like Abacus or ANSYS and do finite element analysis. That's one of the very common next steps you can take. You might be doing material modeling for plastic or composite materials. The same thing, you can take the CT analysis of results and move on to a program like Digimat and use the CT analysis of results as either a verification of your model or just additional information. You might be using CT scan for quality control. Then what you care about is the statistics of the test results. Again, you can do the same thing. You test multiple components using CT and take the results to a program like QDAS for QC statistics analysis. If you're interested in those next steps you can take, I would recommend the Volume Graphics webinar series. They cover one tool or one application at a time, and they have a wide variety of next steps that you can take. If you're new to GD&T, by the way, there are really good introduction YouTube videos called Infinity MFG. If you just look at GD&T Part 1 and Part 2, I think those are about 15 or 20 minutes videos. You can probably get good idea of what GD&T is and where it can be useful. Okay, so you just learned some keys to metrology using X-ray CT and analysis techniques, and we also took a look at a number of metrology application examples. As always, all images you saw today were collected on the Rigaku X-ray CT scanners. And if you want to learn more about them, please go to rigaku.com and contact us. If you missed the previous webinars, I mentioned some of them during this episode. If you missed them, you can go to this URL. I think Tom can put this in the chat. Or you can simply go to Google or YouTube and search for Rigaku CT webinar. That should take you to the list of recordings. Okay, well, thank you very much. Now back to you, Tom.
All right. Thanks very much, Aya. Excellent presentation. So we do have time for a short Q&A, and we've had a couple of questions come in. And the first question is from Stephen, and he asks, are voxels always cubes? And might there be cases where non-cubic voxels would be valuable?
I'm trying to picture what non-cubic. Oh, I guess you mean that your voxel is not a cube, meaning that the XYZ dimensions are different. If that's the case, I can't think of when that's a better way to do it. But if that's the voxel, shape you happen to have, that should not be too big of a problem, assuming that none of the XYZ dimensions is too long or too large. But one thing to be aware of is that if it's not cube shaped, that means that your resolution and accuracy can be direction dependent. In the direction the voxel is long, you have less resolution or lower resolution into that direction. So that's something to be aware of.
Okay, very good. Excellent. Okay. And our next question is from Sarah, and she asks, how does a cone beam configuration affect the measurements?
Actually, it affects the measurements in many ways.
Yeah, so we may have to get back to her with a treatise on this. But if you have a couple of quick comments.
So the biggest one to keep in mind is that when you use cone beam geometry, there are a lot of kind of skewness that happens in the magnification process. So this is why it's important to evaluate the accuracy of your system, because no simple cone beam system is going to be error-free. So it's about knowing what the error is and correct it. That is the important part. When you use a cone beam, you definitely have greater errors compared to the parallel beam, for example. But to look at larger components, in many cases, you're going to have to use cone beam geometry. So the effect, I guess, the number one effect to remember from metrology is that know that there are errors you have to correct.
Okay. Our next question is from Dan, and he says, do you know if Aviso can do or will be able to do similar surface analysis as you've presented today?
I do not know, because I don't have a whole lot of experience with Aviso. My guess is they might be able to do ISO 50 surface determination and some simple measurements, but maybe not GNT analysis, but I might be wrong.
Okay. All right. And we've got a question here from Ted, and that is, he unfortunately joined us late, and he missed on the question of what special features do we need to use to take advantage of the GD&T features? What special software do we need to use to take advantage of the GD&T features?
To do GD&T analysis, I would recommend VG Studio Max from Volume Graphics. As they claim, this is more or less the industry standard for GD&T analysis using X-ray CT. Okay.
And then this is actually an interesting question from Jacob. And the question is it possible to measure the stress on a pipe rather than just the von Mises stress via CT, essentially? Or is von Mises stress the best way to express it?
Well, Mises stress is a simulated stress with the force assumed. That's what I showed in the webinar. If you are going to load some force on the pipe while you do X-ray CT scan, this is an in-situ stress-loaded CT scan. If you do that, you can measure the deformation of the pipe and calculate the stress. But if you're thinking about a pipe that has gone through some sort of process or stress and it's retaining the stress, then you would have to do residual stress measurements. And that is not by X-ray CT, but you would use X-ray diffraction to measure that.
All right. Okay. All right. This looks like this might be our final question, unless a few more come in. It's from Jeremiah, and he's asking, is there a good resource for comparing X-ray CT beam systems? For example, comparing flat and cone, parallel beam, etc. I'll let you answer that, but I think I know the answer.
You can always compare them if you have access to both types of systems. But generally speaking, especially for laboratory systems, I believe that the parallel beam X-ray CT scanners can deal with the relatively small samples. So for millimeter, micron size object shape size analysis, and they might not be suitable just because of the sample size wise.
Right. Okay. All right. So that seems to be all the questions that we have. So let's see here. All right. So as I had said earlier, a recording of the webinar will be available tomorrow, and an email will go out to all of the registrants with instructions on how to view the recorded presentation. And lastly, as I mentioned earlier, at the close of the webinar today, you'll be automatically redirected to participate in a survey about our webinars and what topics you'd like us to discuss in 2021. If you're not able to fill out the survey today, you'll be receiving an email with a link to the survey tomorrow. And again, your feedback is greatly appreciated. And links to the resources mentioned today will also be shared on the landing page, and they'll be located on the YouTube page for this video as well. Thank you again for joining us, and we'll see you all in 2021.